Okay, hello everyone, and welcome to PyData Manchester for our second ever online meetup. Oh no, I'm muted. Oh no, it's all falling apart. It's not falling apart. This is exciting. Okay, I believe we're okay. Thank you very much for joining us for our second ever PyData Manchester meetup. Still, even though I didn't realize it, audio issues free. Today we've got some talks from John and Kelly, which we'll get into. And yeah, so welcome everyone. If you want to get in touch with us, tweet us at PyDataMCR, and you can join the Slack at the tiny URL link, and you can find our podcasts at the podcast link. First of all, I'm John. Behind the scenes, although you can't see him today, Joe, Jennifer, and Sean are all working very hard trying to make sure this goes smoothly, and I'm trying to make sure that it also does. If there's any issues around code of conduct or anything else, please do contact us on Twitter. We're all available on there. If you look at the PyData Manchester meetup, PyData Manchester Twitter page, there's links to each of us if you want to speak to us. We've also got an anonymous response form as well. We take code of conduct very seriously. PyData is a professional meetup and should be treated as such. So if you see anyone behaving inappropriately, please do get in touch. Upcoming events, we've got PyData UK next week. In conjunction with all of the other PyData chapters across the UK, we've got Dynamic Web Page speaking all the way from California on TensorFlow probability, which sounds fantastic. We've also got Ian Oswald. I'm sorry, Ian. I don't know how to pronounce your name. And we've got Ian, one of the organisers of PyData London, talking about high performance pandas and I believe Dask as well. And we're also fingers crossed going to have some introduction talks from some of the organisers from Edinburgh, from PyData Southampton and PyData Bristol. On the same night, our good friends Open Data Manchester are doing an OpenStreetMaps talk. On the 6th of May, we've got our code night. So we're trying to transition from doing this in person, where it makes a lot more sense, to online, where everyone can still get involved, but it's much more community focused. People can bring along their own problems they're working on, ask for help and help others. That's the key thing. Her Plus Data have got an event on the 14th of May. Python Northwest are doing an event, and I can't remember what the date is. But towards the end of May, and Python Northwest always have fantastic events. And for our next event, PyData Manchester, and we're doing a neural networks workshop on the 27th of May. So all these be fantastic. Please do get involved. As I mentioned, we've got some PyData Manchester podcasts. Recent episodes involve interviewing the chaps from Open Data Manchester, which is a fantastically entertaining conversation. And we had an issue discussing recommendation systems, what new advances and all kinds of cool stuff on that. It's obviously a favorite topic of mine, but I did find it a lot of fun. If you're looking for a job, if you're organising a meetup, if you've got anything to promote, please join the Slack and mention it in there, or alternatively, tweet some of us. If you've got any announcements and you want us to shout it out during this podcast, message one of the channels, and if we see it before the end of the recording, then I'll make sure to shout it out at the end. Thank you very much, Lucy, for mentioning. The next Python Northwest event is on Thursday the 21st. Thank you for sharing that. If you want to get involved as a speaker, as a podcast guest, anything else, contact us. So, as I mentioned, tonight's panelists, we've got John Stott from Manchester Airport Group, who you can find on Twitter at NamelessJohn. And we've got Kelly Loukatou, I'm sorry, I'm not sure how to pronounce your name, from Energy Systems Catapult at Angeliki LK. First of all, So before we move on straight onto the talks, there's a few sponsors we need to thank. Horsefly Analytics and Cathcart Associates, NumFocus, who make all of PyData all of PyData possible, and that's both PyData, the organizations that we so much enjoy, but also the PyData stack as well. They really help make an awful lot of open source software usable and available, alongside with the help of the software contributors as well. And we'd also like to thank Google developers. So thank you to all our sponsors. So first speaker, we've got Kelly, who's going to be speaking first. Kelly is a power systems engineer and received her PhD from the School of Mathematics of the University of Manchester in 2019. She's currently working as a modelling analyst in Energy Systems Catapult, a non-profit organisation aiming at accelerating innovation in the UK energy sector. Her current work specialises in optimization, data analysis and visualization with applications in the operation of power systems. Some examples of this include battery energy storage studies, techno-economic impact of low-carbon technologies on power networks, and prediction of wholesale electricity prices. So we've got, make sure. Kelly, over to you.
Okay. Hello. So thanks, John, for the introduction. And I hope everyone is well and safe. So yes, today I would like to give you a brief description about the task I was working the last period, which is more related to weather data. So before that, a few details about myself. As John said, I'm a power system engineer and I graduated from Greece, from the National Technical University of Athens. After that, I stepped into Manchester and then I did my PhD there in the School of Mathematics. And then I graduated last year and I joined Energy Systems Catapult. I work there currently. I am a modeling analyst. So Energy Systems Catapult is a non-profit organization. As John already said, the idea is that we try to identify innovation in small and larger businesses in the UK and accelerate it. So what I'm going to do is, before starting explaining more about the specific data set and how it was analyzed, I'm going to give you a brief description about the project and the specific details. So as you can see on the left side, we have the UK map, and the different icons that you can see is the different distribution network operators that we have in the UK. So basically, in the way that that works, we have the different generators. For example, that may be either a gas or a wind generator, and they produce electricity at a certain voltage. Then that is stepped up to transmission. We have the higher voltages, and then that goes down into distribution, lower voltages, and then that reaches eventually your home. So as you can see at the area around London, we have UK power networks. So that is the specific network operator that is maintaining the network on the London and at the outer area. I'm going to show you another map in a while. And basically, what they asked us to do is, because in the UK, you know that we have this net zero commitment. So since last June, that became legal. So that means that until 2050, we need to go net zero emissions. They are quite concerned that because of that, we are going to start to electrify heating and transport. And that means that we're going to have to integrate into networks a lot of electric vehicles and a lot of heat pumps. And of course, that is going to have a significant effect on the network, as you can imagine. So basically, what they asked us to do is to do that analysis. And as part of that, we need to go into the deeper detail of modeling the electric vehicles and modeling the heat pumps. And as you can imagine, in order to go into the deeper detail of modeling a heat pump itself, you need temperature data. And that's where the task that I'm going to describe comes about. So they said that they are interested to exaggerate and take the worst case scenario, and that basically means that they want very, very low temperature profiles. And I'm not sure if a lot of people are aware, but in the year 2018, we had the beast from the east in the UK, and that means that we had consequently 14 days that we had very, very low temperatures. So basically, as I said, we want temperature data. On the right picture, what you can see is the area that the distribution operator that I mentioned, UK Power Networks, cover. And the specific interest is to model that penetration in the blue area that you can see, okay? So they were quite specific, as you can imagine, about the data and the type of data that they wanted. So they wanted hourly data, not daily data. I already touched the period, so that was January and February 2018. They wanted data, as I said, for this specific area, and also they wanted the data to be open. And that is something that I'm gonna briefly touch around. So in my company, since last September, we have changed a bit the approach that we take towards obtaining the data. So we made the commitment that whenever we can find open data, we are going to accept the fact that we may need a bit more data manipulation and a bit more like time initially paid to do anything that is required to bring that data to the specific format that you require, rather than keep paying thousands per year to buy the data set in probably a ready format. Now, what was happening was that we had some temperature data in the past, but even if we would pay 10K per year, we realized that, again, as you can imagine, there were missing data, there were some unusual spikes out of nowhere. So you can imagine that if you have temperature profiles that they have 25 degrees and then 27 and then 28, when you see something that is like above 50, you can imagine that that is not realistic and that is that needs to be removed. So eventually we were paying for the data sets, and because of the filtering and the different data cleaning, we were ending up with quite a reduced size. So we said we're going to start using open data, but always by checking the license and by checking that we comply, because as you can imagine, a lot of our projects are commercial ones. So for the purpose of this and meeting all the data requirements that we had about that project, my search showed that NASA has quite a lot of data, atmospheric data, and you can find a lot of different data around the globe about wind speed and also temperature. So there was this project, this MERA2, that basically the idea was that you collect all of this data, and then these are, as you can imagine, satellite data. And then basically you have like a very big data repository that has the data, the atmospheric one, for the whole globe. And that is the one that I'm going to explain how I manipulate it to extract the data. So here I have some information for people that they may want, and they may want to access the data themselves. So first of all, I'm not sure if you are familiar yourself. I was not myself when I first encountered that. So the data they are given in, not in, I guess a lot of people that are familiar with Excel format or something like that. So the data they are given in a less common format. So it is the network common data form, and that is version 4 currently. And that basically started back in time, and it was an attempt of the different atmospheric scientists to start sharing data of that big size across each other. So the data, they are all of them stored into a big repository. If you would like to access them yourself, the only thing that you have to do is that you need to go and you need to create an Earth data account. And then the moment you do that, that is relatively straightforward. You can follow the link and create an account yourself. And then the moment you do that, you need to go and associate the specific repository that I mentioned here into your account so that you are able to access the data and then start downloading what you want. Now, going into a bit more detail into the data that you want. So basically, the first thing is that you need to check the documentation and you need to see all the different tables that are available. The moment you do that, you're going to find, for example, in my case, a table with a specific name that has inside the temperature data at 2 meters. And then basically what you do is you visit the repository and you start find the data that they are under that table, and then you start download that data from the online archive. Something else that I am currently working as well is how you can basically automate the process and subset the data. So instead, for example, of downloading the whole globe and then for all these variables extract just the temperature, basically go and do that yourself from the first place. That proves slightly trickier in the way that the repository is being set up, but as I said, I'm currently working on that. So here what I have done is I have extracted a bit of code to give you a bit of idea. So as you can imagine, as I said, that was not a typical format that you use. From what I understood from the website is that you use this because you really try to compress the data. So these are basically data files that are quite big. So there are 400 megabytes, and that is only for one day for all the variables that you have. And of course, there are some online converters. I didn't investigate a lot time into that because you're going to soon realize that it is not free and it is not very efficient because, you know, it takes a lot of time to upload the file and then for the conversion, and then it is a very manual process. So as with a lot of stuff in this life, there is a Python module that can help you to retrieve the useful information out of that file. So here I have just extracted only a tiny piece of code to give you an idea of how the data sets are structured and what is it inside and how you really extract the useful information that you want. So you have, as I said, this net common data form version 4. So that is the module that you have, and you need to import the data set. You can see, for example, here, there is an example that is the 22nd of February 2018. So again, that is all of the different variables for any combination of latitude and longitude on the globe, okay? So if you import this data, and you can see that the only thing that you use is dataset function and just the file name. If you try to print, I have just shortened, honestly, you get back a very long list of information about that dataset. But the important thing that you need to see is that basically you have, as you can imagine, longitude and latitude, as I said. So these are just one-dimensional arrays. And then you have also all the other different variables that, as you can see inside that data set, there are, for example, temperature at different meters, wind speed at different pressures. So all of the different atmospheric data. Okay, so you can see that basically these are kind of three-dimensional arrays. That means that you have the time, and that means that that is 24-hour values because these are hourly data. And then you have latitude and longitude. So basically what you do is you firstly extract the longitudes and then latitudes, and then you have that. And then as you can see here, you need to extract the temperature at the 2 meters. And right now, what you have done is you have from all these different variables of the dataset, you have one specific variable, but that specific variable, which is your temperature, is basically all of the different daily profiles for 22nd of February for any combination of latitude and longitude in around the globe. So basically what you have to do next is you need to find the specific dimensions and coordinates for the area that you want, and you need to extract the data that you want for that date and all the other dates that are of your interest. But that Python module is honestly very, very helpful, because even if the days, as I said, the data sets are very, very big, you can just do the whole process and extract all of the useful data with relatively few lines of code and in honestly a matter of seconds. So I think that is pretty much when it comes to the data set and the structure that you have inside that. So as I said, you have to deal with multidimensional arrays. And the other thing that I have to say is that in the way that this data set works, the longitudes and latitudes, there are kind of masked arrays, and you need a bit of manipulation with a NumPy library so that basically you retrieve the data as well. And you do that with a compressed function. So the next thing that you have to do, so as I said before, until now, you have the temperature, which is one specific variable for the whole number of variables that you have. So as I said, you extracted that, and now what you want is to start extracting even deeper information, which is the temperature at specific coordinates. So the way that you're going to do that is you need to do interpolation to get data. So as you can see that map, as I said, you have extracted all of these different temperatures, but basically now you want to go and you want to focus in the UK. So the first thing that you do is from the inspection that you've done before, you can see that the latitude has 0.5 degrees resolution, okay? And 0.625 resolution is the resolution of the longitude. So now what you do is, if you're the user and you give a specific latitude and longitude, what I have to do is I need to go and find where inside that one DRA that one sits, and then I need to basically extract and interpolate to get the temperature. So to make that a bit clearer, imagine that you gave me a certain latitude, okay? So what I have to do is I have to go and find the point before and the point after, and I have to do the same for the longitude. So I have the point before and the point after, and for each of the points before, I have a 24 hour time series, and I have the same for the points, the latitude and the longitude after the one that you as a user inserted to me. So X1, X2, Y1, and Y2, as you can imagine, those there are the different latitudes and longitudes before and after, and the Q values are the temperature that you have extracted. So what you do is you start the first hour and then you interpolate. So you do bilinear interpolation and you get the temperature in between that set of latitude and longitude, and you iterate until you finish with a whole day, and then you iterate further until you finish with a whole period. So the moment you do that, and you have now gone from the globe to UK, to the specific area, and to the interpolated time series that you have, as I said, for the specific latitude and longitude, then you also need to observe that your data are in Kelvin, and you need to go and convert that to Celsius, which is relatively straightforward. It's just a formula. And then the next thing, of course, is you need to start visualize a bit what data you have extracted so far. So what I have done here is I have extracted, as I said, for the purpose of the project itself, we are more interested into the East Anglia data, but I have just extracted different ones just to show that if you give a specific set of latitude and longitude with the algorithm, you can extract any data set that you want back. Okay. So basically, you can see that here you have for the whole day, for each hour of the day, the different daily profile, and this is 11-day hourly profile. And as you can see, as I was saying initially, you can see that when you go down and you see the pink, so the pink lines, they are kind of the starting date, so 28th of February, and you can see that we really had very, very low temperatures. And that, for the purpose of the project, is going to mean that it's going to make the heat pumps underperform. So basically, they will struggle, and the coefficient of performance that they will have is going to be relatively low. And that means that in order to hit a specific set points, they will have to consume even more electricity. And that means that if they consume more electricity, that is going to have an even higher impact on the network. And that's how the whole story fits together. So the last thing before you finish is that for the purpose of the project, I really don't want the daily profiles individual, but I really want to merge them and create a whole time series. And that is what I have done here. So basically, you take those days and you just tag one after the other. And then what you do is you create different temperature profiles for different areas. And then that profile is what you get for the model that you're going to develop further. And it's going to be kind of an input for your heat pump modeling. So as you can imagine, as I said, from the point that you get the data, there is, thank God, a Python module that can help you to extract the data quickly. As with everything, you need to manipulate a bit. That means you need to interpolate a bit. You need to do some conversions. You need a lot of pandas libraries to help you with the data manipulation. But eventually, from, like, as I said, all of this data, which is important that there are open data. That means that, as I said, you can freely use them even for commercial projects. You get the temperature profile that you want. And I think that's it from me, really. If you have any questions, I'm more than happy to answer them. Thank you.
Thank you very much, Kelly. That's really interesting. Yeah, so I guess, do we have any questions from either Slido or from YouTube? If you got any, if you're watching on YouTube, then feel free to pop a question in the YouTube chats. So look here. So I think one of the things I was a bit curious about, like, because you're using so much memory and it's in such a compressed format, did this library you mentioned, does that help on how you can use the data when it's in memory? So when you're doing interpolation, you've got such a large amount of data. How does that work? Is that covered by the library, or is that covered by other tools?
So do you know when you're gonna do the interpolation, you are sorry, can you hear me?
Yeah.
Yeah, okay, sorry. So yes, when you do the interpolation, you have to keep in mind that you have already extracted the useful data that you want. So that means that you don't need the whole data set anymore. That means that you're gonna just work for the interpolation only with a temperature profile that you extracted.
Right. Okay.
So that means that you're going to have a 24 like profile hour before and one after, but you're not going to have, because the whole data set is so big, because honestly, you have different variables that you really don't want, so you drop them out. And eventually, what you do is you only stay with the temperature of the 2 meter. If you remember when I was showing, when you were inspecting what is inside that data set, there are many variables, because these are like a whole data set of atmospheric data. But what you really want is you extract the temperature and then you drop anything else. So yes, so I mean, that's at least how I do it. I haven't noticed like any memory problems, but I can imagine if you have to do the process probably for months, then you may do. But as I said, what I do is I extract the temperature and then I don't do anything else.
That makes sense. That makes sense.
Yes.
I think filtering down from such a large set of variables to just a few would certainly save time, and memory
Yes.
especially. So we've got a question from James. Thanks for the talk, Kelly. Do you know how the temperature data is generated? Presumably it's based on a model and not actual measurements at all those points?
Yes, I think there is kind of an estimation there because these are, yes, are kind of satellite data, and there may be some like some kind of measurements, but there may be an estimation. So I can imagine if you would have data from like Met Office or like other, you may observe some discrepancies. So what I mean is, if you have different models and you examine the same period, you may have some discrepancies. But again, I wouldn't expect that those are very, very significant. But yes, it is. There are more of estimated data rather than, I guess, real-time measurement, because as you can imagine, that would be very tricky for like the whole globe.
Yeah, of course.
Yes.
So we've got a question from Anonymous. What libraries did you use for analysis and visualization?
So I used pandas for quite a lot of the data manipulation. As I said, for anything that has to do with arrays, I mean NumPy, and again PyPlot for like the visualization. But I can imagine it is a matter of preference if you would like to use something else. But these are the ones. I mean, especially pandas quite a lot because, I mean, as you can imagine, you can do a lot of flexible like stuff in honestly a line or two of code. So yes, that is the main one that you use for the manipulation, and then PyPlot for the visualization.
Cool. Thank you very much.
No problem.
I believe, unless anyone's got any last minute questions, I think that's everything. So thank you very much, Kelly, for joining us and sharing your work so far. We've spoken beforehand. You're okay to share your slides and share your code?
Yes, that's all right. Yes.
Cool. So that will be on the PyDataMCR GitHub at some point. If you
Yes.
bear with us just for one moment, we're going to get John's talk set up and we'll be back ever so shortly. Okay, and we're back live now with John Stott, who's going to be talking about data science with Python and Airflow. Thank you, John. Go ahead.
Right. Hello, everyone. Thank you for coming to this talk. I guess I have no idea how many people are actually here, but thanks for that introduction, John, and thanks for that excellent talk, Kelly. So today I'd like to talk to you a bit about running data science with Python and Airflow. So I work for Mago at Manchester Airport as a senior data scientist, but we're a fairly small data team at the airport. So I end up doing a lot of work with sort of infrastructure around the data, as well as the modeling around that data. And indeed, some days I spend far more time playing with the infrastructure than doing any amount of data science. So what I'd like to talk to you through today is sort of what do I mean by why might you want to use Airflow? What is Airflow? And then a few pieces of best practice to kind of get you started with using that. So for this talk, we kind of have this idea of what is a model when it's in production. And there is one definition of production, which is as soon as someone else depends on that piece of code or that piece of work, then that work is in production. But for the purposes of this talk, we're probably talking about something slightly more formalized than that, something that you can run reliably and repeatedly. And for those kinds of projects, quite often you want to run them on a schedule. And if you're familiar with Linux or Unix, you might be familiar with the kind of stars and numbers on the side of the slide here. And this is cron syntax. The idea is you can kind of specify your schedule by specifying the minute that you want it to run, the hour, the month, the day of the month, and the day of the week that you might run. And by using different combinations of numbers in these different fields, you can specify a surprisingly flexible number of schedules. So that first line would correspond to we want to run a project every minute of every day of every month. The second line is perhaps more useful, and it's we want to run a project 1 minute past the hour, kind of every hour. And then finally, that bottom line would be some kind of a daily schedule where at 8:05 in the morning, we want to do something. And cron is actually fine if you just have one project that you want to schedule, and you have a Linux machine to schedule that on. But generally, once you have one project that is using a schedule, you will tend to find yourself in possession of many projects that need some kind of a schedule. And worse, you'll tend to find that some of these projects have kind of dependencies on each other. Like, for example, you might have one piece of work that kind of extracts some data from somewhere, and that has to sort of run and then put that data somewhere else. And then you have another project which is going to read in that data and then perhaps do some modeling with that and make some predictions or do some estimation or whatever that project is doing. And so how you kind of manage that in a cron world is, say that first project runs at 2 in the morning and takes about an hour to run, then you kind of end up with the situation where you go, okay, we'll schedule that first thing at 2, we'll then wait an hour, and then maybe we'll add on an extra hour's padding. And so we'll schedule the next project that's going to use that output at 4 in the morning. And that works fine until that first project either really, really overruns for whatever reason, or alternatively, it actually fails because that second project will still try and run. And this might mean that it then makes inferences on old data or that falls over, or any number of other potential failure scenarios. Plus, when you get to multiple cron jobs, it can be quite hard to keep track of that kind of success or failure, and also any output, because cron mostly relies on emailing the system email rather than anything more modern and user-friendly. So Airflow is a project that aims to address some of these issues and quite a few more. And so Airflow is a project that is now an Apache Foundation managed project. It was originally contributed there by Airbnb, but it's now maintained by a wider group of people kind of across the data science, data engineering community. It's written entirely in Python, and you can get it by doing pip install Apache Airflow. And that community that maintains it is fairly active. There's a release of it now around once every month or two. And the idea behind Airflow is it's a workflow scheduler rather than just a sort of task scheduler. So what you end up working with are these things called, well, DAGs, or directed acyclic graphs, but workflows essentially. So for that situation where you have like related projects, you kind of say, so this particular workflow here would start up here at the top with this spec check, and would then run this task. Then all of these check tasks here could be run in parallel. They don't have to be, but they could be, because they don't depend on each other. And then we'll run this fit models task. And then finally, we'll run these two downstream manifest tasks. And this is an actual DAG from one of the projects that we run at the airport. And this screenshot is, and this sort of snap of the screen is actually taken from from part of the UI that Airflow provides. So the idea is we can kind of, rather than just having one task, and that task in cron could be a script, but that script will kind of grow linearly. We can instead start to express what needs to be done in terms of do this, then do that, then maybe do any one of these things, then we go into the kind of next task, and so on. So you can express quite complicated dependencies. Now, these workflows are made up of sort of two components. So operators are the things that actually do work. So for example, there is an operator to run SQL queries. There's another operator to run tasks in a Docker container. There's yet another operator that will copy a file from one location in S3 to another location in S3. And there are a whole raft of kind of very specialized operators that you can use to save you from having to write the same kind of boilerplate code over and over in what might otherwise be a much more free-form Python script. The other sort of thing that makes up an Airflow workflow are sensors. So sensors are tasks that don't do anything except to watch and see whether a condition has been met. And these are most useful when you're interacting with kind of other systems outside of your control. So if, for example, you are interacting with some kind of legacy data warehouse in some other part of the business that sort of like at the early hours of the morning sort of does a whole bunch of computation on the previous day's sales or whatever. Now that might be ready at 1, it might be ready at 2, who knows really? Like those things can sometimes be quite variable. But if you have a sensor in your Airflow DAG, you can kind of check, like, is yesterday's data ready yet? And if it's not, then you can hold up the execution of the DAG until of the rest of the workflow, the rest of the DAG, until that data is ready. And there are sensors, as I said, for running SQL queries, sensors for checking whether a file is in S3, sensors for checking that a task in another DAG has run, which is sometimes useful for kind of splitting stuff up between different workflows, so you can run them a little bit independently. And sensors are, yeah, as I said, really great if you have to because of decouple your DAG from some external dependencies so that you won't end up running with stale data or proceeding on blindly when things aren't completely ready. And so with this knowledge of what a task, of what an operator and what a sensor is, we can, well, the other thing that, sorry, yeah, I'm getting a bit of myself there. One other thing that Airflow offers, which is quite nice, is you get this UI and dashboard that kind of has the different DAGs, what schedule they're running at, what the status of recent tasks in those DAGs are, and you can see kind of these ones have succeeded, this one failed. We also get when this thing last ran and a kind of capsule summary of the last few DAG runs that's quite useful if, for example, well, when you come in on a Monday morning and want to see did everything run over the weekend, or when you come back from a week's leave, you can kind of check and see, like, has everything all run as expected? And also through this DAG, you can get that visualization of the workflow. You can dig into logs, those kinds of things. It's all available through this web UI. Building a workflow is writing some Python code. So we start out with some imports. This is then default args kind of get passed into every task. So it's quite useful for putting shares, stuff like the start date, a default number of retries, that kind of thing. Then we create our DAG, which is kind of with this DAG, which is called example, and this is running on a cron schedule still that says at like 13 minutes past 5 in the morning. What we're going to do is we have two tasks. So we have this key sensor task that is going to check to see whether the data is there. And then we have this Docker operator that's going to run this Python script that will take the kind of input path and output path and will presumably do some very, very smart data science with those files and then produce some predictions that it's going to save to S3. And then to specify the dependencies, you sort of use the bit shift operator here to say T1 depends on T2. And so what this will do then is when it runs, this key sensor will first run, and as soon as data.csv exists for today's data, because you can interpolate in dates with this, it will then run the Docker operator that will run this Python script, and if those succeed, then Airflow will show green. If they fail, then this task will be retried once, and this Docker operator will be retried sort of 3 times before finally Airflow concedes that it has failed, which is quite useful if the process might be a bit flaky due to network issues or whatever. So there are a bunch of other helpful features that Airflow gives you. So as I mentioned earlier, Airflow will kind of collate the logs that your tasks provide and make them available through the UI, so you can dig into why a particular task went wrong or just see what happened. It also has this notion of connections, and connections store stuff like, for example, details of how to connect to a Postgres database or a database. or how to authenticate with Amazon or Google. So, and the idea is then you can use this connection in the DAG so that the DAG doesn't need to have any any usernames, passwords, those kinds of credentials that you really want to keep out of version control. You can instead manage them through connections in the Airflow instance. It supports alerting, so out of the box, Airflow will email you if stuff goes wrong, but it's relatively simple to also set it up to, for example, let a Slack channel know that something has gone wrong. If your Airflow instance starts to grow bigger, you can use Celery to start to distribute tasks out to workers on many boxes. And also, one thing that we make some use of at the airport is this idea of an SLA. So you can say, for example, this task must have completed within, or this DAG must have completed within 4 hours of it starting. If it hasn't completed within 4 hours, it will let you know, but it will still keep executing it. So rather than a timeout being like a hard cutoff, you must have finished by now, it will instead just notify you that it's taken so long, but without throwing all of that work away. So you can, for example, let people know that some dashboard hasn't been refreshed or whatever. And there are a whole bunch of other features that you can find out through reading the documentation. So I'm now going to go on to talking through a few bits of best practice just to get you started. So first of all, use operators where you can. As I said, there are some very generic operators like the Docker operator that will just run anything that you can express as a command in a Docker container, which is, if you're familiar with Docker, really sort of anything. But there are a lot of specialized operators that can help, because code that's in an operator is code that you don't have to write and maintain yourself. If you do have scripts to express like more generic tasks, like for example, model fitting or some complex data processing, for example, something like the data that Kelly was talking about would be a great fit for something that you could run in Airflow potentially. If you do end up with that situation, I would suggest you package your scripts up in containers to keep all of their dependencies together with that script, rather than installing an increasing laundry list of libraries and other utilities on the Airflow server directly. You'll find that the dependency management problem can get out of hand quite quickly in that case, and Docker just removes a lot of those issues. I'd also suggest kind of to keep business logic out of the DAG file. So keep your DAG file as like a very, very high level. We're going to run this task, then this task, then this task, with relatively few details about what this task actually is in the DAG file. So for SQL, you can write your SQL in a separate file. For Docker, obviously, that is already kind of, you're just running that script. And this then keeps your DAG file quite a bit shorter, which then makes it easier to navigate and easier to see what is happening in there, and leave the details of the how to the things that the task is running. And finally, remember that DAGs are Python, and I'm sure a lot of people on this call are very familiar with Python as a programming language. And the DAGs are Python. This means that if you can more clearly express the code that you need to write in Airflow using a loop or using some features of the Python standard library, then do that. You can do that, and you can make your DAGs and the DAG code look a lot clearer. Also, by that same token, please do keep track of your DAGs in some kind of version control. I'm sure you will find that that makes your life a lot easier. So in summary, I hope I have convinced you that you can use Airflow to manage workflows with dependencies between tasks. But even if you're not doing that, the fact that you get centralized logging and centralized alerting can sometimes still be worth it, even for those very, very simple workflows. I say Docker is great for packaging up tasks in a workflow, whether you use Docker directly on the Airflow server or whether you actually end up using something like AWS Batteries, what we use at the airport, or Kubernetes or whatever to execute those containers, sort of package your complicated scripts up in Docker. And also Airflow has a lot of features, and it is very easy to get kind of lost in that noise when you start out with it. So start small, get something working, and then kind of add in that complexity. But Airflow is not that hard to get started with. So I hope you found this talk as useful as an introduction to Airflow and why you might want to use it. Thank you.
Thank you very much, John. That was fascinating. Certainly, I've got some ideas about how I can get Airflow get going with Airflow at the moment in some of the projects I'm working on, where operability is not great. And like you say, I'm a data scientist in receipt of one production task. Therefore, I'm a data scientist in receipt of many, many production tasks, and cron isn't quite cutting it. So let's go to the questions in Slido. So can Airflow send out diagnostic charts as part of the alerting, or is it limited to a message?
So the UI itself does have various diagnostics and timings and which tasks failed. As far as I'm aware, it doesn't send, like, I certainly haven't found the setting that configures it to send that out, although how I have the Slack alerting set up, you do get a complete copy of the DAG. So you could write the code to do that, but I'm not aware of a simple plugin for that right now.
Fair enough.
If you want to write it, please let me know. I will gleefully use that kind of thing.
Oh, it sounds really popular then. So I'm aware of Composer, which is I think Google Cloud Platform's managed version of Airflow.
Mm-hmm.
Are you aware of any differences between kind of a basic Apache Airflow and Google Cloud Composer?
At Mago, we use AWS pretty much exclusively, so I've not actually used Composer at all, so I can't comment.
Fair enough.
On that.
Okay, no worries. In terms of, like you mentioned, source control, do you have any kind of insight into preferred source control and continuous integration with DAGs? Because I do understand that can get quite complicated.
Yeah, so testing DAGs is one thing that Airflow does not make as easy as I would like. But on the other hand, quite a few of the errors that I found you can actually expose just by, for example, checking that the Python code actually runs in the DAG, for example. That actually gets you quite a way towards checking, is that DAG valid? There's also a link which I didn't put in the slides, but I will edit after to put in, that talks about some slightly more comprehensive tests that you can run to, for example, check that you do actually have a acyclic graph, which is to say it has no cycles in it. You can end up sort of accidentally giving yourself dependency cycles.
Infinite loops.
Which, well, Airflow will then just complain when it actually tries to schedule it, as far as I'm aware. But obviously, that's not going to run, so you kind of do want to check for that. But yeah, testing workflows and testing that they have the correct dependency relationship is not trivial.
Yeah, sure. I mean, there's a lot of externalities, external files that you really, you can't test.
Yeah. But on the other hand, you do get quite far just by checking that actually your DAG is valid Python and that running that DAG file throws no errors.
Sure, that makes sense. Couple of people have upvoted this. You did mention it's easy to get started with Airflow. What's a good way of getting started with Airflow? Are there any tutorials or anything you can recommend?
So the Airflow website has a tutorial. Also, as sorry, I've just seen Joe in Slack. Also, as of the latest release of Airflow, they've now started to provide Docker containers that have a complete Airflow install all set up. So I've not actually tried those, but those are probably a reasonable place to start. But like by default, if you just want to check that it works, if you pip install Apache Airflow and follow the tutorial, it will be running using the sequential operator that you probably don't want to run actually in production, and it'll be saving stuff to SQLite, which again, probably if you have more than yourself depending on this, you probably don't actually want to do that. But you'll at least be able to show that your DAGs execute and task dependencies are respected and that kind of thing, and get a feel for how the UI works and how connections work and all of that. But yeah, the site does have a sort of brief tutorial on how to write DAGs and that kind of thing.
Cool. We'll make sure to put a link out with that as well. One of the last questions, although there's still time to ask questions if you have any. Do you think Airflow will kill off Luigi, or do you think they fill different niches?
Tough question. I see them as really very similar tools, and you've also more recently got Dagster and Prefect that are all kind of in this same space of Python workflow specification libraries, frameworks,
workflow
technologies. I've not seen, despite all of their different projects like Claims, anyone with a kind of definitive, yes, definitely, this is the only one. It's a complete superset of all of the features of all of the other ones, except in their project marketing, obviously. So I guess it would be nice if there was more work on a common thing, but on the other hand, I know that Luigi handles data dependencies slightly different to Airflow, and that might be more important to you than other things that Airflow offers, which is a very wishy-washy way of saying, I don't know.
I mean, I think you're almost certainly correct by saying it depends, just because that's almost always true. So Yeah, just got a question from James saying, thank you for the great intro to Airflow. So not so much a question as a statement, but appreciated nonetheless.
I will take that.
Yeah, and well, you should. It's a sentiment I can definitely echo. So I think that's all we've got time for today. Thank you to Kelly. Thank you to John. Share this talk with all your friends. It'll be available on YouTube. We'll be sharing Kelly's slides. Hopefully, are we able to share your slides, John?
Yeah, I'll send you a link to them.
Cool. We'll be sharing John's slides too. So any questions, you know where to find John, you know where to find Kelly, you know where to find the rest of us. Thank you very much and see you later.